So there are vulnerabilities that you can systematically get out of your programs, right? If you have cross-site scripting problems, you use a templating engine that knows during variable substitution what the context of the output is to do the proper escaping automatically. Boom, you don't have to do it manually in your code. SQL injections. It's a miracle for me that stuff like that still exists out there, because it's very easy. Use prepared statements and boom, presto, SQL injection problem's gone, because output escaping is done in the right place. And for buffer overflows, it's a little bit harder. Like you can just use not C. But I was looking into systematic approaches, and I found a scientific paper about how to make C buffer overflow proof, and I worked with that, and that's what I'm going to present here today. So you probably all see the problem. Raise your hand if you understand where the problem in that code is, please. Anyone? You all speak C, right? Who's programming C? Who knows how to write C? Nobody? 1, 2, 3, 4? Okay. So I might actually have to explain the problem then, I see. You have a buffer here, which is 16 bytes in size. We're getting in an argument, and the argument is a string. It's a pointer to a character, and with this loop, this is copied into this buffer here. So the problem obviously is that this loop goes on as long as the argument is, and it might overflow the buffer here. And if that happens, you can exploit it, right? You can write into a memory area where you're not supposed to write to. And that's something that hackers call a buffer overflow, maybe a stack overflow or heap overflow, depending on where it is. So science calls the problem of spatial memory safety, because in memory space, you write into the wrong part of memory space. And by doing that, you can exploit it in a lot of fancy ways. There's another problem. Probably see, memory is allocated, memory is freed, and then it's accessed, which is a typical use after free bug. And that's also usually exploitable, because the data structure that you're writing to suddenly is the linked list of the memory manager, and you can do fancy stuff here to exploit the situation. Same for that second free. That's also wrong, because it's a double free. Double free vulnerability can be exploited. This problem is called because you're accessing the right memory, right? You're not actually overflowing anything, you're just accessing memory at the wrong time. So science called that temporal memory safety. So what are approaches to get rid of those problems? So the first one is obvious, like use a safe language. Don't use C. Use a language called not C. It's like the no SQL of the programming world is don't use C, ever. Except for when you have a really, really good reason and you're a really, really good coder. And we will have a test in the slides, and if you pass the test, you're allowed to write C. Most people don't. You can use mitigations like randomizing the address space, preventing data from being executable, using stack canaries, etc., etc. All those make life of an attacker harder for actually exploiting a vulnerability. They don't address the underlying problem of temporal or spatial memory safety. Thing is, there are always workarounds for the mitigations, right? You can use return-oriented programming to work around DEP. You can use read vulnerability to defeat ASLR and stack canaries, etc., etc. And it goes as far as not always requiring code execution for an attacker to get what he wants. There's an undisclosed technique that was presented at Kansec West, or rather it was not presented. The guy was winning the Microsoft prize for IE, exploiting IE 11. And so he had a couple of blurred slides because Microsoft said, please don't show that. But I recognized one of the windows in the blurred slides, so I guess I have a good idea what's going on there. What happens is that when you have a web page in IE, it runs in a trust zone. So for instance, it's local and trusted, or it comes from the internet. And that's a variable that's somewhere in memory. So if you can write to memory, You can maybe write to that point and suddenly flip on the God mode bit for the web page. Presto, you can do whatever you want without actually getting code execution in a traditional sense in the browser. Quite a lot of memory debugging tools exist. Most people have heard about Valgrind, probably even used it. GCC and LLVM have something called a memory sanitizer. There are a number of scientific projects that work in that direction. And there are two general approaches on how these tools work and try to find bugs in the problem. So, a little word on notation. I'll be showing C code here. Black is the code that the user has written. Red is the code that has been compiler generated. That's usually the tools don't actually generate C code. They work on an intermediate representation. So this is just for readability. So because I hope most people are able to read C. So what a lot of those tools do, stuff like Valgrind, like the memory sanitizer, is a so-called object-based approach. They have a way to figure out for a certain address whether it's okay to write to the address or not. So I write to an address in memory here, or I read from it. Before I do it, the pointer is checked on correctness. So I keep a table somewhere. Valgrind uses guard pages, etc., etc. So just some way to figure out is that memory accessible or not. Thing is, this has limitations. Like if you have a struct where there's a buffer in the beginning and then a value that you might want to protect in the end, then if you have a buffer overflow in this buffer, you're writing right into a value that you might not want the user to be able to write to. And the object-based approach can't detect that, because obviously if you allocate such a structure, that's all valid memory from beginning to the end. So techniques like Valgrind, like memory sanitizer, won't detect that situation, and it's still bad. So the other approach that a lot of the academic tools are using is a so-called pointer-based approach, where for every pointer that you have in a system, you remember extra information. You remember so-called base value. This is the original base address of the object that was pointed to, and a bound, which is the other end of the buffer. Right? You have a pointer which might point right in the middle of an object. Like if you allocate an array, you can take the address of the 20th element. And in that fat pointer approach, you still remember where that array started and where it ended, so that when keeping increasing the pointer, you know when you hit the end of the buffer and can raise an error. The pointer-based approach has a number of issues. One of them is that suddenly your pointers increase in size. And so your structure layout starts to break, reading binaries where you just have a struct defined breaks, etc., etc. So the softbound CTS project was, from all the projects I've looked at, the one that deals the most with practical problems, with actual practical problems. So it uses so-called disjoint fat pointers. I'll explain in detail what that means, how it is implemented. It's essentially pointers, so the meta information for pointers is kept around in different places. So your layouts don't change, your stack structure doesn't change, and things will keep on working. It implements two modules. Softbound is the spatial safety. CTS is the temporal safety. The whole thing is implemented as an LLVM optimizer pass. So you link it against LLVM, it works on the intermediate representation. And it even comes with a correctness proof, which has flaws. I get into that in a couple of slides. But for now, they have shown that their method actually eliminates 100% of all spatial and temporal memory safety issues. So, how does it work? Okay, more advantages. Source code compatible. You can just put in your source code. You can use separate compilation. So quite a number of the other academic projects require all of your source to be in one big C file, which of course is not manageable for real-world code. The overhead is low. It slows down your program by a factor of 2. And yeah, it finds all the bugs and not just some of the bugs. So this is what it does. I access a pointer here. Again, that's the user-written code. And a check is inserted before that pointer access. So for the pointer, I have the base value and the bound value, which are passed around actually as extra variables inside the intermediate representation. And of course, the size of the object pointed to, so I can decide whether I might be at the very end of my buffer, and the thing I'm accessing is big enough to overlap a bit with my buffer boundary, so that's why that size is also passed in. Okay, easy enough. This is what the check looked like when I found it. Anybody seeing the bug in that? No, I told them that they proved correctness of the implementation, which means they proved that they're inserting checks all at the right places. But the check looked like that. Nobody? What was that? No. Okay, here's the thing. If you don't see the bug in there, don't write C code. Just don't. You won't be able to make it secure. So they obviously didn't prove the correctness of the check. And I'm reminded of don't Knuth here. That's the solution. You have an integer overflow, right? Whoever said integer overflow wins. The thing is, this addition here might overflow and then be smaller than the bound value, even though we're writing over the end of the buffer. So yeah, my first contribution to the project was making that check actually work. Okay, where do the base and bound values come from? On allocation, the base is initialized to be the address of the pointer allocated. The bound is the pointer plus the size of the object. And if malloc failed, we make sure that our bound value is also 0. So we can fail when somebody is trying to access a null pointer without having a check before. You can allocate objects on the stack as well. If you do that, in the function prologue that's emitted for the function, the base and the bound are initialized to the addresses on the stack. So pointer arithmetic is where it gets tricky for usual C programs, because as soon as you do that, your classic implementation loses any information over what kind of object you're referencing. So when I generate a new pointer in my code, again, that's what the user writes. He accesses takes the address of an element in the array, or he just adds the pointer plus an integer value to get a new pointer. That new pointer also gets a base and a bound value, which is initialized to be the base and the bound of the base pointer here, of the pointer on which the arithmetic operation is based. So if I have something allocated at address 100 of size 100, I know that my base is 100, my bound is 200, and if I say pointer value plus 50, new pointer gets the value 150, but it gets propagated a base value of 100 and a bound value of 200, just like the point it was based on before. It becomes obvious that you can do pointer arithmetic to the outside of the buffer and back again. That works. So you can say plus 500 and then minus 500, and you have an intermediate pointer that doesn't point inside the object, which is actually legal according to the C standard. And then when you have calculated it back, you can still access the buffer in a correct way. So this is a very interesting special case when I take the address of an element inside a struct. I need to narrow my base and the bound. So that means if I'm taking the address of that struct element here, I want only that part of memory to be my new object that I'm having base and bound values for in order to prevent the intrastructural overrun into other elements here. Of course, I can also do that for an element of an array inside a structure. I have to do more narrowing here, another special case. You're not supposed, you don't need to understand that in detail right now. Just know that the software takes care for you. Storing and loading pointers is a tricky thing because we have that base and bound metadata. So far, we have just passed it around as extra variables, as phantom variables inside the function. But sometimes we load a pointer from memory. And as I said, memory layout doesn't change. So we need to get our base and our bound value from somewhere. And this is done using a table. So we have a table that's indexed by the pointer. And we just load the base and the bound value on loading the pointer from memory. So these are the local variables introduced. We load a pointer from memory. We load from a table our special values that we need to do the check. The table gets populated when you do the other way around. When you write a pointer to memory, then the table is populated with the base and the bound value for that very pointer. That's not terribly efficient. Actually, the biggest source of performance penalty inside the whole project. So in order to speed things up, the base and the bound values are introduced as phantom arguments to your function. So you call a function with one argument. Internally, that function gets converted to getting 3 arguments. And the base and the bound value, which we know at call site, right? For that PTR, we have a base and a bound. They are passed inside here. So the called function also has the base and the bound for the argument available without having to store them in a table and load them from a table. There are quite a number of details that need special care, like global variables need to be, they're global, so they're not allocated on the stack or using malloc, so there needs to be a special mechanism for making sure that base and bound values exist for those. Memcopy is tricky because memcopy is actually a primitive in LLVM, so LLVM recognizes that you call memcopy and calls its own internal version of memcopy instead. So there's special code that detects that situation and calls a wrapper that checks the arguments instead. You need to treat function pointers in a special way. Creating pointers from integers is something that's in some situations tricky. So it sometimes works, you can cast around stuff, and when you roll it into memory as a pointer and then turn it into an integer, you can shift it around, reassemble it again, it will be in the table. But in some situations it won't. There's a very fancy trick for implementing doubly linked list, for instance, using only one field. Which means you have your structs for the doubly linked list with one pointer. You have a pointer, a separate pointer pointing to the first element and to the last element of your list. And inside that single pointer value in your struct, you store the forward pointer XORed with backward pointer. So when you come in from the beginning, you know what the first address is, so you can use an XOR to get the pointer value to the next object out of that. And use that value in turn as XOR on the second one and the third one, etc., to traverse the linked list. If you do that, it breaks. Obviously, the software CTS can't cope with that kind of trickery, so it's unsupported. Casts, unions, var args all need special tricks. If you want to understand what they're doing, go read the paper. We don't have the time to go into detail on that. So let's get to temporal memory safety. Again, we're using fat pointers here, so we introduce 2 additional values we keep for every pointer. This one is called a key, and the other one is a lock address that we now keep around with PTR like we did in the spatial case before. The key is just a unique value. Every time an object is allocated, for that allocation, a unique key value is generated. Also, that key value, a lock is allocated. We remember the address of the lock, and the key value is stored at that address. Also, we keep that in the map again. On deallocation, we write an invalid key value into the log, which is a piece of memory, right? We allocated that. Of course, first we check before freeing, we check whether the free is okay. So we are looking up the key value and look whether that's the pointer it's pointing to, so whether it all makes sense, then we can free it. On pointer access, what we do is we check whether the key value matches the value stored in the log address. Remember, on free, we are setting that to invalid. So instead of, if the object is correctly allocated and we didn't call free yet, then that key value will match the value stored in the log. So the key matches the log, we can turn it around and open the pointer. If there is a different object at the same address that has been freshly allocated, this will now have a different key value. So using key and log, we can make sure that the object is temporarily okay, that it has been correctly allocated and not been freed yet. The rest pretty much looks like the situation in the spatial case. So for pointer arithmetic, we need to keep track of the key and the log address. On load from memory, we have a table where we look up the key and the log address values to propagate them into the variables. If we store a pointer to memory, guess what? We also save the key and the log address in a table. Globals don't go away, so they get a special magic global key value and a global log address that we can reuse for all the global stuff, because globals are always there. They're not a problem temporarily. The biggest problem with the approach there is that it's not safe in case of threads. So if you have multiple threads, you get race conditions between one thread freeing the thing and the other thread not having the updated meta information yet. So threads are bad, but you know what? If you look at shared state, that's always a problem. If you do proofs in mathematics, in computer science, once you have shared state, you run into problems. You get all sorts of, you know, race conditions, deadlocks, etc., etc. So I would advise going the Erlang way. Don't have any shared state between threads at all. Send messages. It makes things so much nicer and easier. Same goes for shared memory. Obviously, when you have shared memory, you no longer know who owns which side. If two processes are communicating in a shared memory segment, you don't know which side owns the object. So that's bad. So, but as long as your single-threaded stuff works. So you might ask, I've been telling about the project for quite some time now, what's my contribution to it? Other than fixing the check, right? I sat together with a friend and we streamlined the code very much. We introduced function attributes that trigger using the different calling conventions with the extra arguments that trigger introducing checks as processing of the function body. And the original project actually had a list of libc functions and wrappers for them inside the module. And if you wanted to call external libraries that weren't compiled with softbound CTS active, you'd need to go into the LLVM module at that function name, recompile your compiler, which of course doesn't scale, right? So our goal was to take that academic project and bring it to a point where you can use it for real-world code. And we decided to use FreeBSD for the simple reason that it is able to compile itself completely using LLVM. So every single line of C code in your program goes through that compiler and you have it available in source. So it was a nice basis to play around with. So we started porting softbound CTS to FreeBSD, cleaned up the modules. We started instrumenting the libc, which essentially means implementing the right thing in the allocator, right? Malloc and free are no magic. They need to come up with the right base and bound values, propagate them. You have a couple of assembler functions for performance reasons where you have to manually write the checks because assembler code isn't translated. So we did that. And the good news is that the proof of concept works. So we have a sort of hello world that actually finds buffer overflows. And I'd like to show that to you. Here we go. So that's a FreeBSD system. And I have that little test code here. You can see that's a bit small. I hope that's still readable. So you see that's a function like the one at the beginning of the presentation. A array of size 16 here. And we copy stuff into the array, which is passed in as an argument. And we're using the first command line argument here. So we're taking first command line argument, argv1, pass it to function foo, and copy the text into a buffer of size 16. So obviously, when you run that, what would you expect to happen? You'd expect the thing to crash, right? And press return, it should crash. Why? Because I'm accessing a command line argument that I didn't pass. What happens here now is that software doesn't crash. The invalid pointer access is detected instead. So softbound CTS tells me you violated memory safety. I see here it's pointer value 0 with a base and a bound value of 0, so a null pointer that I access. That's bad. I can pass an argument here. Now it doesn't crash. Why? Because the argument I pass is short enough to fit inside that buffer here. So let's see what happens if we make that really long. And again, softbound CTS detects the memory safety violation and aborts my software. So demo successful. Now, yes. Okay, so the code for that is online. This is the original author's webpage. This is my tree with our modifications. I'd like to use the opportunity to thank Hannes Mehnert for giving me support on FreeBSD. He was the guy who actually knew how the build system works, which files to touch, etc., etc. And of course, I thank the original authors for providing such a nice piece of technology and for patiently answering my questions. And with that, I'd like to thank you for your attention, and I'm answering questions now.
What is the runtime penalty in time, probably, of running with softbound checks and without them?
I haven't done any substantial measurement myself. The original authors ran the spec benchmark, and they claim to see if you turn on all the features like spatial and temporal safety, both for reads and for writes, you end up with a factor of 2. So it's half as fast as it was before. So that's 18 months of Moore's law. If you consider the fact that people out there use Ruby for web servers, I think we live in a time where we can trade a little bit of performance for a massive increase in security. More questions?
And well, are there any measurements on how much more memory you need to run the code?
No. So obviously you need 5 times as much memory for the pointers in your code. So the question really is how much of your data are pointers, and that depends on your software, obviously. So once the thing is, it now compiles a bit of the FreeBSD world, so it compiles libc, it starts compiling a couple of other libraries. It doesn't support C++ yet, because it fails on the instruction that invokes a vtable pointer, which also means that I cannot really compile any meaningful real-world code. Like you obviously would want to compile Mozilla with that, right? That would be a viable goal, and I'm not there yet. But once I'm there, I'm going to do that kind of measurement, obviously. More questions?
Just one question. Why did you decide to develop just another tool for soft bounds, assuming that we have already successful products like CLang++ with different kinds of sanitizers, and we have also sanitizer for the newest version of C++, I mean for G++, okay? And both of them works with C++.
Yes, I mentioned the sanitizers at the beginning of the talk. They incur quite a performance overhead, so they're good for debugging. They're not good for actually deploying the solution in the field. That's number one. Number two is that they use the object-based approach. I also explained that. So for an address, they only remember whether that's a valid address or not. So they don't understand that I might be writing to an address that is properly allocated, but is not the object I was allowed to write into. So there are overflow situations that the memory sanitizer won't find. Whereas that solution finds 100% of the overflows.
What about Linux IOCTLs that modify the state of the memory? Do you describe the IOCTLs somehow, or do you copy them from Valgrind?
So this is FreeBSD, not Linux. So I think things work a little bit differently there. So the question, how does the interface to the kernel world look like? So the good thing is there is very little actual allocation or deallocation going on when you do a kernel call. So syscall looks like a function call to a native function. And you already pass in memory that you allocated yourself in most of the cases. So quite obviously, if inside the kernel it writes into a part of your memory that you passed that's not okay to write to. So you allocate a 10-byte large buffer, pass that to a syscall, and tell the syscall to write 100 bytes into that. That's something that would need to be manually checked. So that's where limits are in kernel interaction.
And what's the underlying structure for the lookup table?
It has changed one or two times. I think at the moment it's a red-black tree.
Okay, thank you.
Okay. No more questions? Then thank you very much. And if you come up with more questions, you can find me in the hallway. Thanks.
Thank you very much for your lecture.